So let's move to part 2 of laws of motion. And this time we'll deal with the topic of constrained motion. And we'll take up a typical example, a simple example, which is relevant for mains point of view. So this is a kind of pulley arrangement. And what we need to find here, we need to find, let's say we need to find the acceleration of 1 kg mass, 4 kg mass, and even this pulley also in motion. These are three objects which will move. Each of these objects will have some acceleration. Let's find, if you have to find any of this, how would you go about? What is the constraint? So this here, since they are connected here, what we identify here, there are two strings. I hope all of you can notice here, one string runs like this, it runs around this pulley, it runs around other pulley, and connected to 1 kg mass. And this is second string. So whenever we have a string like this, a string pulley arrangement, constraint is based on the length of each string remaining constant. So we have to somehow use, so motion of connected objects will be such that length of the string will not change. So how many equations we can form? We can form as many equations as the number of strings. In this case, there are two. And that's what let's use. How do we make use of this condition that length of string does not change? There are a number of ways of using this constraint. So let's use one particular method, which is, I think, easier of all the methods. So what we do here, let's focus on this part is easy. If this length of the string is constant, it means what will happen? Whatever motion 4 kg object has, same motion this pulley will have. So velocity, displacement of and acceleration of pulley and 4 kg mass will be equal. So that's the condition we can use for this string. Other important which is more relevant is this string, and this string also we notice if you look at this string, we can think of one straight part, second straight part, third straight part, and the part of the string which is wrapped around the pulley. So these are the 5 parts we can identify as, and let's see how do we deal with it. So what we do, we mark this force. This is one part is connected to ceiling and the point of tangency on the pulley. So this string length will depend on point of tangency on the pulley and the ceiling. So if the pulley moves or the ceiling moves, the length of string will change, not otherwise. Okay, so this point is not in the string. Point is on the ceiling here. Point is on the pulley here. So there's a string. There's some particular length of string here. Second length is, again, this is between point of tangency on the pulley, this particular point on the pulley, and this point of the pulley. And this length will change if either or both of the pulleys move. And which is the third part of the string? This is the third part of the string, which is between pulley and the block here. If again either of the two moves, the length will change. So what we'll identify here, the principle what you're going to use here is something like this. If both the objects move, so let's say, in case of displacement, and then we can arrive at similar relationship in velocity as well as acceleration. So let's say if 1 kg mass moves like this, it has from initial position, if you look at, it has a displacement of x1 in the upward direction. And naturally we can here is easy to, we need not necessarily know the direction. In this case, we know if this moves up, this has to move down. So we have marked the direction, assumed direction. So our relationship we are arriving at based on this directions, x1 and x4. Suffix indicate the mass, kg mass. So these two quantities are related. And let's see how do you find relationship between the two. And whatever relationship we have already mentioned, displacement of kg block, same as displacement of pulley. So this also will be x4. The pulley also will move from here by how much? By x4. The motion of the pulley. Now, what is the constraint here? No change in the length of string. It means either net change is 0 or increase is equal to decrease. Either way, we can form equation. And whenever this increase, we can write as plus change, and whenever decrease, we can write as minus change. Now let's focus on this part of pulley. What has happened? This point has not changed. This point here has moved down by x4. Pulley has moved down, so the point of tangency also moved down. So this length of, since this point has moved by x4, there's increase of plus x4. Middle string, this point has not shifted as this pulley has not moved. This length also increased by x4. This second part of the string is x4. And third part here, this part, the block has moved up. So this point has moved nearer to the other point. Hence the length will decrease by minus x1. Suffix indicate the block number. We have ignored other two parts, but the part which is wrapped around the pulley, those part length will remain same. We ignore those parts. We will take only the straight parts of the string. So these are changes. So net change, if I add all three together, it should come to 0, or twice the displacement of 4 kg block should be equal to displacement of 1 kg block. That's what the equation comes to. Twice the displacement of 4 kg block is equal to displacement of 1 kg block. And if we differentiate this relationship twice, this is a linear relationship. If this has happened in time t, we divide by time t, it becomes velocity, and then we can, based on differentiate, we get acceleration. So whatever relationship we get in terms of ratio based on the constraint, we can have a similar relationship on the acceleration also. So how do we use this relationship? So this additional condition comes from the constraint. So A1, this acceleration in magnitude is twice of this. So if I call, if the block 4 has an acceleration in the downward direction of A, this will have an upward acceleration of 2A. Whatever value we assign here, it would be twice of that and in the assumed direction. The relationship is positive, it means we assume direction, we can continue with this. We don't have to reverse any direction. This will be equal to 2A. And now it's easy to solve. What is this A equal to? Now we can write acceleration of 4 kg block. Will equal to, if we take downward direction positive, 40 Newton. And let's mark the tension also. If this tension is T here, this whole string everywhere tension will be T. So this also will be T. This also will be T. And now we consider equilibrium of this pulley. Net force on this pulley has to be 0. It means this has to be 2T. And this has to be 2T. So these are the forces. Now we can form this equation between, based on this taking as this as system and this as the system. What is A equal to 40, which is positive, minus 2T by 4. And the second equation for 1 kg block, we can form what is 2A equal to. Now we take it conventionally is easier to take the direction to be positive in the direction of acceleration. So upward force positive, which is T, and minus downward force, which is 10. We are taking G as 10 divided by mass M. So we have two equations between A and T, and we can easily arrive to value of acceleration and tension. So this is a way to solve, one way to solve. And this is a pretty easy way. We can also do terms of velocity. Velocity also will remain same. Let's take a question which is slightly more challenging here. And this system, two blocks are shown. Each has mass M, block A and block B. And the system is released from rest. If the acceleration of block A and B soon after release are A1 and A2, then what is the relationship between magnitudes of acceleration? Of course, directions are different. So what is the relationship between, whenever this have this kind of equation, relationship between magnitudes of acceleration? See here, see in this case also, whenever it is released from rest, even it is inclined, we will not prove it, but whatever relationship we have in for acceleration, similar relationship exists in case of velocity. Why are we going for velocity? Velocity is easier to understand. What is the relationship between? So if I take rather than acceleration, if this block soon after, little time after release, if this velocity is v1 and this velocity is v2, so whatever relationship we arrive at between velocities, similar relationship will exist in between A1 and A2 for a time interval very soon after release, so that this angle theta has not changed much. Angle theta has almost remained the same. So again, we solve based on the length of the string being constant. Now, which are the parts of the string? This is one part of the string from here to here, and second part of the string. So string between a block B and the P. So in this case, if velocity is v2, okay. So if velocity is v2, what is the velocity of approach? Now I'm solving based on not displacement rate. Sorry, not based on the change of length. I'm solving based on rate of change of length. What is the rate at which this point is moving towards this? What is the point? So if this point moves as a component in this direction, so the length of string will shrink. So rate of shrink is what we done in case of displacement, similar thing we do in terms of velocity. If velocity is v2, it's component along this length. So velocity of approach of this point will be equal to v2 cos theta. So that's a rate of decrease of length. And if this length is decreasing, this length has to increase. This point doesn't change. So if this point is moving velocity v1, so this point is moving away from this point with the velocity v1. So we can say the rate of increase of length of this part is equal to v1, and rate of increase has to be equal to rate of decrease. So that's the relationship. v1 is equal to v2 cos theta. We could have also done in terms of displacement. If we take a very small time interval, what will happen soon after a small time interval? This point would have moved here, and in very small time interval, this displacement x, or let's call it delta x, would have been equal to v2 into its delta t, and delta t is approaching 0. So if this is the displacement here, so in this case, what is the change in length? This is forming a triangle. So what I will do here, I will redraw this triangle in slightly different form. I'll place this one something like this. Let's make the blue color line as horizontal. So this line is like this, because when we draw in a proper orientation, it becomes slightly easier. This is my blue line, and this point I'm drawing it here. So from here, the red line also starting. This is the in place of a red color line, the new position of the string. This is the initial position, this is the final position. And this part here is the displacement. And you notice this angle is an acute angle. This is blue line, so this is an acute angle. This is equal to V2 delta T. This is, let me call this point as A, this point is B, and this is B dash. This is A, and this is B, and this is B dash. You'll notice here, this kind of thing we have done in case of YDC also. This angle is going to be very small here. This displacement is small. So this angle is very small. If I drop a perpendicular from B dash, we drop a perpendicular, then hypotenuse and base will be almost equal. Theta is close to 0. So in this case, what is the change in distance between AB? Initial distance was AB, now distance become AB dash. So difference will be, since AB dash is equal to AM, now the difference is equal to BM. And what is this BM equal to? This angle is theta, this angle also theta. So BM is nothing but the component of displacement along line AB, which is equal to V2 into delta T. So what is change in length which has happened? Change in length is equal to MB, and MB is equal to V2 delta T into cos theta. So this is change in time delta T. What is rate of change? Rate of change in length between the 2 points here, which we call as velocity of approach. Rate at which distance between 2 points is changing. So rate of change or velocity of approach between 2 points, we divide by delta T, it becomes equal to V2 cos theta. This way also we can understand this what we written here. Let's again, one more point we understand, which is applicable in many cases. If we understand it well, many places we apply. In many cases, we come across question where pulley itself is under motion. So this is a pulley here, and this 2 blocks is connected to 2 blocks with the string. And all cases will take the string is to be tight, is taut. The string is taut, it means it's not slack. All condition we are solving, that string doesn't slacken and string is length is not changing. So we can, what is the relationship between 3 velocities here? And whatever relation exists in the velocities, similar relationship on taking a derivative, we can find relationship between acceleration. Let's see how we calculate velocity. In this case, we try to understand this in slightly different way. What we do, we write coordinates of endpoints of the string, wherever the string is connected to block. So I write this coordinate of the point where the string is connected to block as y1. This point is y1, this point is y2, and this particular height is yp. This is whatever coordinate center of pulley has, this end of the string also has the same length. So what is the, can we write the length of the string in terms of coordinate? Let's see that length of the string. Left string is yp minus y2. And sorry, I have missed y. One is y1, one is y2. So one string is yp minus y2. Other side string is yp minus y1. So add these two, that's the length of the string. Again, what we have done, this part of the length is not changing. We have ignored the length of the string, which is wound around the pulley. And this is the total length, which is constant. So if we take this derivative, basically I could have written what is yp equal to, yp is equal to 2yp is equal to y1 plus y2. And if y1, if objects are moving with certain velocity, so derivative of the coordinate will give you velocity in the y direction. Here motion itself is taking in the y direction. If I take its derivative, velocity of the pulley is half the velocity of v1 plus v1 and v2. Other way of saying, what is the velocity of that pulley? It's the mean of the velocity of this point and this point with sign. All have to be, we have to use the sign convention. And we can extend this logic here. So differentiating again, we'll get a relationship between acceleration also. What is acceleration of the pulley? Mean of acceleration of two objects, string is connected with sign. There's another important point we can make use of. Not only is it not necessarily to the block. How about if we take a particular point on a string here? Let's call, but we call this point as A. And if I take another point in the string, doesn't matter where, it need not be at the same level. If I take point B, whatever velocity v2 has this point on the block, this point also has the same velocity. And this point also velocity same as velocity v1. So whatever relationship, we can also say what is velocity of the pulley. Velocity of the pulley is average velocity of point on the string on the either side. So this is something we can also like. Velocity of pulley is average velocity of this string particles on either side of the string. One on this side or one on this side. And let's take a case where we apply this particular concept here. So here what we find, and whatever velocity, sorry, one thing I mentioned, and same velocity, if this exists for velocity, same relationship exists for acceleration also. Now come to this case here. What is given here? This block A has some acceleration. We'll substitute this value here later, but since the directions are given, we'll go by the direction which is mentioned. Okay, this is A, this direction of acceleration of A. And this is the direction of acceleration of C here, AC. Direction of acceleration of B is not given, so we'll assume that direction and we'll solve consistent with the direction. So let's assume this is direction of acceleration of B. Now, since it is pulley and there are two strings here, if I take 2 points A and B here, let me call it not A and B, since B is already there, I'll call this point as small a. This point is, sorry, let me call this point as P and Q, because E is already there, C is also there. This points are P and Q. So if I had known acceleration of P, and if I had known acceleration of Q, I can find out acceleration of B. But do we not know acceleration of point P? See, if this point moves with an acceleration of AA, of course, this string, this part of the string will move down. Whatever motion this particle has here, same motion this particles of the string also will have. Very simple intuitive sense. So this will have a downward acceleration of AA. And since here this is moving away, so every particle on the string here, if I look at the particle, if you look at whatever acceleration this particle has, which is same as the block here, this particular particle on the string also will have same acceleration, this particle also same, which is equal to AC. Right. So that's the relationship here. Now we have this block has the same acceleration as pulley. Now I can relate this acceleration with these two. And what is this acceleration equal to? Let's go consider imaginary points. We consider two imaginary points. And we found the respective accelerations. Okay. Now let's form an equation. Now these are the acceleration AA and AC. These are the 2 points. Now what is the equation? How is the acceleration of A is related to A and AC? This relationship is AB is equal to half AC plus AA with sign convention. And all three we have to use same convention. So I have taken upward as positive, so AB value, this is AB value I have written as dV by dt. Why I written dV by dt is this question relates to velocity also. So acceleration of B, which is equal to d by v dt, is equal to 1 by 2. Acceleration of block C acceleration is 3, substituted 3. But A is in the downward direction, that's why I have to put minus 20. So this is the value we get here, or what we get here, dV is equal to 1 by 2 t minus 12t dt. Now what we need to find? We need to find time when the block comes to rest again, which means initially velocity of B is 0. Again we have to find at what value of t. So at t is equal to 0, velocity of B was 0. So we have to find what is the value of t so that velocity at t is again equal to 0. So we can use this equation to find out. So we'll integrate from where to where? 0 to t. Which 0, 0 here, this velocity is v. At time t also we have taken time t such that this velocity is 0. So thus integration we have, and now it's very easy to solve. If we integrate, this term left hand side comes to 0, and this equal to 1 by 2, and this will be equal to 3t minus 6t square is equal to 0. So from here we find two values of t. Of course, 1 has to t is equal to 0. So this equation we get here, and one root is t is equal to 0. Initially, the velocity of b is equal to 0, and the second equation will come 3 is equal to 6t or t is equal to 0.5. At 0.5 second, again this block will come to rest if this kind of motion is given to block A and C. So very simply we can solve. So these are some examples of constraint motion, and we'll continue with some more later on. So I'll stop here and we continue with the rest in the next session. Thank you.